Okay, so now, how does this all tie together into what we ultimately care about, which is, do we have a polar molecule or do we have a non-polar molecule? So first, let's talk about what do we mean by that. When we talked about polar bonds, okay, polar covalent bonds, we're talking about a bond between two atoms and where we have unequal sharing of the electrons. So one side of the bond is a little more negative because the electrons spend more time around that side of the bond. One side is a little more positive. And that's, again, what we're talking about here. Polar essentially means I have a separation of charge. Okay, I have some area more negative because the electrons are hanging around there more often. Another area of the molecule that's more positive. So here we're looking, and we also use the term dipole moment. Dipole moment is the polarity of a bond, and dipole moment is what we measure if we want to know, well, how polar is the bond. And just as an aside there, this is the unit. A Debbie is the unit they use for the strength of a dipole moment. All right, so let's take a look. Here's why we care about it, because there are some properties of a substance, several properties of a substance, that whether it's polar or not, affects that property. Okay, one of them is that polar molecules will orient themselves in an electric field. Since they have positive and negative sides, they will orient themselves when exposed to an electric field. Non-polar molecules would not. They don't have a positive and negative side. Okay, so this here is looking more at a bond dipole versus a molecular dipole. A bond dipole, again, is what we had looked at before in an earlier unit, where we're just talking about the polarity of a bond between two atoms. A molecular dipole looks at the molecule as a whole, looks at how do all of the bonds in the molecule come together and how do all of those dipoles interact in a way that either we do have one area of the molecule that's more negative and one that's more positive, or they interact in a way where they sort of cancel each other out. We end up where overall we have an equal distribution of charge throughout the molecule. Okay, so here's an example here. Here we have carbon dioxide, and the individual bond dipoles, we are polar. Carbon to oxygen, there is a difference in electronegativity that makes that individual bond polar. Now, when we're drawing those dipole moments, the way that we look at that is we draw an arrow from the more positive end towards the more negative end. And so for carbon dioxide, see how we would draw that there? And if you've had physics and you've looked at vector addition, you can see that these are equal magnitude because the difference in the electronegativity is going to affect the magnitude. So these are equal in magnitude but opposite in direction, meaning there is no, their net force is zero, no net dipole. Okay? On the other hand, if we look at water, for example, here we have, these are our dipole vectors right here, and if we look at how those add up, we do have a net dipole. They don't completely cancel each other out. So we would have a more negative area on this side at the oxygen and a more positive area down by the hydrogen. Okay? So we can predict the polarity of the molecule looking at these things. We're going to look at the electronegativity values to see if the individual bonds have dipoles. Then we're going to look at the shape, and then from the shape we're going to determine whether these dipoles will cancel or not to produce a dipole for the whole molecule, or to make the molecule polar. Okay, here's kind of a summary on molecular polarity. The things that you need to keep in mind when you're answering the question, is this molecule polar or nonpolar? And so basically you're going to look at the outer atoms, and you're going to look at whether or not you have lone pairs on the central atom. So here, if we have our diatomic molecules right here. If you have a two-atom molecule where they're both the same, we have no difference in electronegativity, that's nonpolar. If I have molecules where we have no lone pairs on the center atom and all of the outer atoms are the same, that's going to be nonpolar. Okay, this "and" is very important. No lone pairs and the attached atoms are all the same. So I could have, for example, I might have, and I think we've drawn this one before, say I had CH3Cl. Alright, so there I have no lone pairs, but the chlorine is different from the hydrogens, and so this would be polar. Does not meet both criteria. Polar molecules have to meet either of these two situations here. If we have an outer atom that is different, like the one I just drew, or if there are lone pairs on the center atom. So even if the outer atoms are the same, the lone pairs are going to basically deform the shape to a degree that the dipoles will not cancel out. So the presence of lone pairs on the central atom is going to give us a dipole moment.